Hi everyone. Let's start today's session with a simple thought. When you walk from your home to school, how far did you actually go? Did you just take the total path into account, or the straight line distance? That brings us to two essential ideas in physics, distance and displacement. Imagine you walk around a park and end up exactly where you started. You've traveled a certain distance, but your displacement? That's zero. Let's understand how. Let's define them clearly. First, distance. It's the total length of the actual path a body travels, and we represent it with the letter S. Since it doesn't involve direction, distance is a scalar quantity. It's always positive and simply tells us how much ground is covered. Now, displacement. This is the shortest straight line distance between the initial and final positions of the body. We write it as S with an arrow over it to show it's a vector quantity, meaning it has both magnitude and direction. For example, 5 meters north is a displacement because it tells you both how much and in which direction. Both are measured in meters in the SI system and in centimeters in the CGS system. Since displacement is a vector, we can show it using an arrow. The arrowhead tells us the direction, and the length of the arrow, drawn to scale, gives us the magnitude. For instance, in the diagram, vector P to Q shows a displacement of 40 meters east. The origin P is where the object started, and the terminus Q is where it ended up. This way, displacement becomes more meaningful. It doesn't just say how much, it says in which direction. Let's now compare the two distance and displacement through their key differences. Distance depends on the path taken. Displacement only depends on the start and end points. Distance is always positive, but displacement can be positive, negative, or zero, depending on direction. Also, displacement is always less than or equal to distance, never greater. Example, in the diagram, if a boy walks 4 kilometers east and then 3 kilometers north, his total distance is 7 kilometers, but his displacement is the straight line from the start to finish, which is 5 kilometers, using the Pythagorean theorem. As you can see in the diagram, this forms a right-angled triangle. Let's understand this with some real-life scenarios. First case, the ball is thrown straight up and falls back to the thrower's hand. The distance is twice the maximum height, but displacement is zero because it started and ended at the same place. Second case, a person walks around a circular track and completes one full round. Distance equals the circumference, which is 2 pi r, where r is the radius. But displacement? Again, zero, because the start and end point are the same. These cases show how displacement can be zero even when distance is not. Let's do a quick tabular comparison to seal the concept. Distance is a scalar. Displacement is a vector. Distance depends on the path. Displacement doesn't. Distance is always positive. Displacement can be positive, negative, or zero. Displacement can be less than or equal to distance, but never more. These differences are crucial as we move ahead into velocity and acceleration, which also depend on these two quantities. Alright, let's quickly revise what we've learned today. Distance is the total path length, a scalar quantity. Displacement is the shortest path from start to end, a vector quantity. Distance is always positive. Displacement can be zero or negative. In curved or circular paths, displacement is usually less than distance. These fundamental ideas form the building blocks of motion analysis in physics. I hope this session helped you get a clear picture of how objects move, not just how far, but also in which direction. See you in the next session with more motion-packed physics.